Welcome to Data Mining, Lecture 5, Part 1, Clustering. What is clustering and what is the difference between clustering and classification? Clustering is defined as follows. Given a set of data objects, the clustering process is to group the objects into clusters where similar objects are in the same cluster and dissimilar objects are in different clusters. In contrast to classification, which is a supervised learning process, clustering is an unsupervised learning process because it does not require any predefined training classes. More precisely, clustering does not go through the training phase. It's just an algorithm that automatically groups data objects into different clusters. The key idea for clustering is that we should have a well-defined distance functions among data objects. Based on that distance functions, we are able to identify similar objects or dissimilar objects. Intuitively, similar objects are closer to each other and the distance between them is small. These similar objects are farther away from each other and the distance between them is big, is large. So the core here is the distance function between data objects. For different types of data in different domains, the distance function could be very different. If you want to develop meaningful measures to evaluate the similarity of data objects, that job is not trivial. There are many applications of clustering. Marketing strategy. We can cluster customers based on their profiles. You look at their profiles, you do the survey on customers, and then you know their income, where they live, and so on. And you, based on their products they purchase, then you can say this group of people always buy expensive products. So next time when I have expensive products, I should notify them. This group of people always buy products using coupons. So when I develop new coupons, I send these coupons to these families. This group of people cannot afford expensive products. So you design a different selling strategy. Also, in bioinformatics, we cluster protein sequences into families. In fact, this is how people are doing in the real world. There's a Swiss prot family, this Swiss prot protein database in which they keep like 800 or 900 protein families that they have clustered. They do this clustering based on, for example, what type of motifs a particular protein sequence contains. They define the term motif, and then they use a motif to do the clustering. World Wide Web application, you can cluster visitors of your website based on their access patterns. I can look at the log. Okay, when this person comes, this person always visits my publication web page. So when I have new papers, I can send these papers to this person or this group of people. When this group of people access my website, they always look at the new programs. So these new programs might be interesting to them. So when I have another new program I can send these people for free evaluation and for feedback. So you can look at their access patterns and you can group people, you can divide the people into different groups, and you can have different strategies for dealing with different groups of people. That's why we need to have the clustering process. So the input of a clustering algorithm is usually a set of data objects and the pairwise distances, dissimilarity or similarity among the objects, and also a user-defined parameter value k. That k tells the clustering algorithm how many clusters eventually you would like to have. So the output of the clustering algorithm is k clusters. Suppose in the input you specify that the k is 3, then the output of the algorithm will be 3 clusters. Suppose you specify that k should be 10, then the output of the algorithm is 10 clusters. So we use this value k to control the number of clusters that will be produced by the clustering algorithm. By the way, this is the most generic format, but this doesn't mean that this is universal. This is true for every clustering application. All right? This situation is most common when we deal with clustering. Okay, you develop a clustering algorithm, and that algorithm will take a set of data objects and the distance between these objects, and also parameter value k. For example, k is 5, and then will produce automatically 5 clusters of objects based on their pairwise distances or pairwise dissimilarity values. There are many different types of data arising in many different domains that need to be clustered. For example, we might be interested in clustering p-dimensional points or vectors in Euclidean space. And you all know the Euclidean distance, right? You all know how to calculate Euclidean distance. You could even cluster these students in this classroom based on their geographical distances. You two sit together, so you are grouped together. And so you two sit together, so you are grouped together. And that's a notion of distance. Nominal variables. Nominal variables take a finite number of states as their values. For example, a nominal variable might have red, blue, yellow as its value. So 3 values for that particular nominal variable. Or another nominal variable might have the value deep, shallow. Or another nominal variable might have a value long, short, and so on. These variables take a finite number of values as their attribute value, as their values. Strings, trees, graphs, and other complex objects, sets, bags, and so on are also data objects we are interested in. Most of my research is focused on defining the distances between trees and the graphs, and then cluster these trees and graphs, and so on. So this is another big research area. Also, you might want to cluster data of mixed types. You have trees, you have graphs, you have protein sequences, DNA sequences, and you have secondary structures of protein sequences, and so on. And you want to cluster this data of mixed types, and so on. So now let us talk about some common distance values in the real life. The most common distance in Euclidean space is the so-called Minkowski distance. And the formula for the Minkowski distance is the following. So the distance between 2 data points in the Euclidean space, where the point I has these coordinates xi1, xi2, and xip, and the point j, which is a vector, has coordinates xj1, xj2, xjp, and these 2 points are 2 p-dimensional points in the p-dimensional space, Euclidean space. And that's how we define the Minkowski distance between these 2 points, I and j. Okay? Now, this is a general formula. When this q is 1, we refer to this Minkowski distance as Manhattan distance, which is a very famous distance. So the Manhattan distance between point I and the point J is defined as the sum of the absolute values of the differences between the corresponding coordinates xi1 minus xj1. You take the absolute value xi2 minus xj2. You take the absolute value, and xip minus xjp. You take the absolute value. You sum up all these absolute values, add up all of them together. That gives you the distance, the Manhattan distance between point I and point J. In Euclidean distances, or in the Euclidean space, I should say in the Euclidean space, all the distance values are always positive. So look at this. This is absolute values and so on. But in the non-Euclidean space, or in the abstract metric space, you could have negative distance values. Okay, but that's a different issue. That's basically reporting in a paper we have submitted to the transactions. But in this particular case, for Euclidean space, all the distance values are positive. So you see here, we use an absolute value for the distance, for the difference between coordinates, and then we add up these absolute values together. When Q is 2, the Minkowski distance becomes the Euclidean distance. So you take the square root of this sum of the squares of the differences between the corresponding coordinates xi1 minus xj1. You take the absolute value, you take the square, you add up together, and you take the square root. That still gives you a positive value. So the distance is always positive in Euclidean space. But in other spaces, like abstract metric spaces and so on, you might see different situations where distances are negative. All right, that's a research topic. The Euclidean distance is in fact a metric. What is a metric? A metric is a distance function that satisfies the following properties. For any 2 points ij, for any 2 different points ij, their distance must be greater than or equal to 0. And if they are the same thing, then the distance must be 0. The distance between point I and point I must be 0. The distance between I and j should be always the same as the distance between j and I. And this property is known as symmetric property. Symmetric. The distance from me to you is the same as the distance from you to me. Triangle inequality. The distance from me and you should be always less than or equal to the distance from me to you and the distance from you to her. This is a triangle inequality. And these properties are collectively referred to as metric properties. For any distant function, if that function satisfies these properties, that function is a metric. Okay? Why we care metrics? Many distant functions, in fact, are not a metric, and they are just distant functions. Okay? And therefore, they do not have the triangle inequality. But why triangle inequality is good? In 1990, I published a paper which is together with my advisor, published a paper which is part of my thesis, which is concerned with best match retrieval. The term best match is also known as the nearest neighbor. Okay? Given an object, the best matching object of this object is the nearest neighbor of this object. Best match. Okay? An object that best matches this object. Best match. So that's nearest neighbor. So in that paper, what we do is we use this triangle inequality property, only that property, and then we develop an algorithm so that we can speed up the nearest neighbor or best match retrieval. So given an object and given a database of objects, how do you know which object best matches this object? How do you know which object is closest to this object? Okay, so our algorithm can find the nearest neighbor in a very fast way. And the only property we use is this triangle inequality property. That is, we assume that we only have a metric. And based on that metric, our algorithm can, based on a data structure, our algorithm can find the nearest neighbor so that object, we can immediately identify the object that is closest to the given data object. So the problem is the following. You have a database of objects, and you have a new object. The naive algorithm will calculate the distance between this object with every object in the database to find the nearest neighbor. Now, our algorithm pre-calculates some pairwise distance between the objects in the database. They pre-store there. And when the new object comes, instead of calculating the distance from the new object to every object in the database, we're able to just calculate a few of them, and based on the triangle inequality property, we're able to quickly identify which object in the database is closest to the given object. Okay? And that paper was published in 1990 ACM transactions on information system. Some of you can already understand the underlying algorithms. You have a database of objects, and suppose their pairwise distance are pre-calculated and stored there. Now you have a new object arriving. If you calculate the distance between this object and one of the data objects in the database, so now you know the distance, right? Suppose the distance is 3. And suppose now you have pairwise distance pre-calculated in the database. This is 3. And then suppose now this object is very far away from this object you just calculated. Then by the triangle inequality, you know that this object should be also very far from that object. And therefore, you can prune that object from consideration. So instead of calculating the distance between this object with every data object in the database, I can just calculate a few of them in the database, and I'm able to identify the closest object based on the triangle inequality property, right? If I'm close to this guy, and this guy is very far from that person, so I can infer by the triangle inequality property, this should be far away from that person, and therefore, there's no point to calculate the distance between this new object with that data object in the database. That's right. I don't want to argue with you. I want you to read the paper, and then you understand that. You know why? Because if you look at this formula in a different direction, the formula says the distance from me to you is less than distance from you plus the distance from you to her, right? To you, right? Now, if you look at this in a different direction, that means the distance from me to you should be always greater than equal to the difference between the distance from you to you and the distance from you to me. So in other words, dik should be greater than equal to dij minus dkj. You take this term here. And that is a very powerful tool for us to use to prune the objects from considerations during the retrieval phase. All right? I'm so close to you, and if I know you're farther away from him, I'm able to infer that I'm also farther away from him. You know, something like that. But I don't want to get into too much details. Okay, the paper is published in ACM Transactions on Information System in 1990. You should be able to find that paper. And if you are logging as an NJIT student, you can go to ACM Digital Library from NJIT website. You can go to ACM Digital Library, and you can find every ACM paper in the ACM Digital Library. And you can easily download all the papers you want. These days, I just stay at home downloading all the papers I'm interested in from this ACM Digital Library, and I read them. I don't even need to go to the library. Nominal variables. A nominal variable can take several states. For example, red, yellow, blue, green, and so on. Suppose you have two data objects, and this data object has 3 nominal variables, and this data object also has the same 3 nominal variables. Then the distance between these two objects can be defined based on this formula. P is the total number of variables. In my example, 3. So 3 is the denominator. M is the number of matches. You look at the 3 nominal variables for these two data objects. Look at the first nominal variable. Suppose the first nominal variable for this data object is yellow. The first nominal variable for this data object is also yellow. So that's a match. Okay? Then look at the second nominal variable. The second nominal variable for this data object has the value shallow. The second nominal variable for this data object has a value deep. So this is not a match. Okay? Shallow and deep, they are not matching. Look at the third nominal variable. The third nominal variable for this data object has the value long. The third nominal variable for this data object has the value short. It's not a match. So how many matches you have? Only one. Okay, color. For the color they match. So the distance between them is the total number of variables, which is 3, minus the number of matches, which 1. 3 minus 1, which is what? 2. 2 divided by 3. That gives you the distance between these two data objects. So intuitively, if two data objects have precisely the same nominal variable values, the distance should be what? Should be, there are 3 matches, so 3 variables minus 3 matches, so the numerator will be 0. So their distance is 0. If they look exactly the same, their distance is 0, which makes sense intuitively. Okay?
So each nominal variable has the same weight.
Now here, that's right, a very good question. So you were asking whether we can weight these different nominal variables. In practice, you can weight them, no problem. In my particular example, each nominal variable is weighted the same. Okay. So now so far we have discussed different types of distance values, Minkowski distance, and special cases such as Manhattan distance, Euclidean distance, and also distances for nominal variables. Now, there are also distances for strings, trees, and so on, but those become more sophisticated, and we don't have time to discuss them here in the class. As I told you, developing a new distance function for complex data objects is non-trivial. One of my PhD students is doing a dissertation, and his dissertation is to develop distance measures for phylogenetic trees. And that deserves 1 or 2 dissertations, and you can see how difficult it is. So it's not a trivial subject. Okay? Phylogenetic trees are trees that model evolutions of lives. So it's like tree structures. But how do you define the distance between these trees? So that needs research. And how to define the distance in such a way that the distance is satisfied by phylogenetists or satisfied by biologists. You don't want to develop a distance that doesn't make sense to biologists, right? For example, you could define distance between protein secondary structures, but you have to make sure that these distances make sense in the real life, and they make sense to biologists. Developing distances between protein sequences or protein secondary structures or protein tertiary structures can be well-deserved several PhD dissertations. But the problem is that the topic is non-trivial. Okay, I know you are working with the PDB and you know DALI search engine, so that's a kind of distance. But that distance might not be a metric because that's an alignment between protein structures. Alignment sometimes is not a metric, meaning that it doesn't satisfy the triangle inequality property. But so this area is still research area. In fact, my current NSF grant is to develop search engines and the distances between these graph and the trees. This graph include like protein secondary structures or many other types of data. Okay, so this is not a trivial topic. Now, back to a simple algorithm. The K-means algorithm has been developed long ago, and this is a very interesting algorithm. Now, recently, a lot of people modify this algorithm in their domain. So what I present here is a most original K-means algorithm. And you can modify this algorithm and use that algorithm in your domain. Okay, why you can do modification? Well, if you look at this K-means algorithm, let us look at step by step. The first step is to partition objects into K non-empty subsets. That's why you call this algorithm K-means algorithm. You have this K in the name of this algorithm. So initially, you partition data objects into K non-empty subsets or clusters. So this is a partitioning clustering algorithm. In the future, we will talk about other type of clustering algorithms, such as hierarchical cluster algorithms. Okay, for this particular algorithm, it is partitioning clustering method. Step 2, you compute the center for each cluster. Okay, so initially, you in some sense randomly divide the objects into k non-empty clusters. Step 2, you compute the center for each cluster. Now, how to compute the center, I will show you an example in the next transparencies. You need to use the distances, okay? And because different domains have different meanings of distances, so there, people modify this algorithm to fit their domains because they can develop their new distance algorithms. Then step 3, assign each object to the cluster with the nearest center. Okay? You find some centers. And suppose I'm an object. So among this center, which one is closest to me? That center is closest to me. So I should belong to the cluster with that center. And so on. So in some sense, you reassign these objects to different clusters. Then you go back to step 2. You compute the center for each cluster again. You keep on doing this until there's no new assignment. At that moment, the algorithm terminates. And let me show you an example. We need examples to illustrate the algorithm. Examples always help us to understand things better. So this is an illustration of the k-means clustering algorithm. Initially, you are given 10 objects in yellow and in blue colors, okay? And you somehow randomly group these 10 objects into 2 groups, divide them into 2 groups. So you see, this is group 1, and this is group 2. And by the way, this is random partition. I don't care whether the partition is good or bad. It's just an initial partition. Any question? And then, for each cluster, I calculate the center for that cluster. Now, these are 2-dimensional Euclidean points. So, how to calculate center for these points, for these 5 points? You look at their x-coordinates. You add up all these 5 x-coordinates and divide it by 5. That result gives you the x-coordinate for the center. Similarly, you look at their y-coordinates. You add up the 5 y-coordinates and then divide that sum by 5. That gives you the y-coordinate of the center. The center need not be any of these existing objects. All right? Similarly, you can find the center for this cluster. So now this red dot represents the center for this cluster. The x-coordinate and the y-coordinate is calculated based on what I described to you earlier. Similarly, this red dot is the center for this cluster. And the x-coordinate and the y-coordinate are calculated based on what I described to you. You look at the x-coordinates of these 5 points, add up together and divide the sum by 5. You look at the y-coordinates, add up together and divide the sum by 5, and that gives you the y-coordinate of the center. And then, as you can see, in fact, this center is not any of these 5 existing points. Okay, it's just a hypothetical point. It's just center. Okay, we know that's the center. Then, what we do is we reassign objects if necessary. We reassign each object to the cluster with the center that is closest to that object. So look at this object. Look at these 2 centers you have so far. Which center is closest to this object? Look at this object. This center is closest to, right? To this object. So this object should be assigned to the cluster which has this center. So that object will just reassign to the same cluster. Similarly, you look at this object. Between these 2 centers, this center and this center, which center is closest to this object? Again, this center, right? So this object is reassigned. In fact, remains to be the same cluster with this center. Now, there's something different. Look at this data point, this data object. Among these two centers, which center is closest to this object? We see that this center is closest to this object. So this object should be reassigned by taking it from the cluster 1 and put in cluster 2. Similarly, look at this data object, which was originally in cluster 2. But right now, after you calculate centers, it seems that this object is closer to the center for cluster 1. So that object is reassigned to cluster 1 with this center. So you reassign this blue data point and this yellow data point, okay? That gives you something like this. So now you have two new clusters. And then you calculate the centers for these clusters again. That's a loop, by the way, okay? And then you get the new centers, right? Because you have new data objects in this cluster, and you have new data objects in this cluster. So you have new centers. Now, once again, for each data point, you try to see which center among these two centers, which center is closest to this data point. And then you do the necessary reassignments. It turns out that for this current scenario, we are done because, you know, all these 5 data points are closest to this center and they are in this cluster with this center. And all these 5 data points are closest to this center rather than this center, and they are assigned to the cluster containing this center. So we are done. So now you repeat the calculation of centers, you get the same centers, and you get to try to do reassignment. There's no need to do reassignment, so the job is done. So this is the k-means algorithm. For this particular case, 2-means cluster algorithm. You develop 2 clusters for a set of 10 data points. Okay? So basically that concludes the part 1 for clustering, lecture 5 clustering. In the next lecture, I'm going to talk about more about clustering algorithms. And basically this ends up with a clustering lecture.